Hi Jens, how are you?
Hi Alexis, I'm fine and you?
Fine. I haven't listened to the radio for a long time.
So you have a phone,
Yes.
so you can use it.
Oh, it's so easy, like to mainstream.
Okay, so you have like something else or?
Maybe I have something. An Ethernet cable. A USB cable. An antenna. And Raspberry P4 card. The DVB-T dongle. And the USB stick.
So you have all of these in your pocket?
Yes.
Okay. So in order to modelize, process radio frequency signal, we will use GNU Radio. It's a free and open source software that will allow us to process those radio frequency signals. It can be used with external radio frequency hardware, which is very convenient for our project, considering that we have the hardware. And it can, in the case that we don't have any hardware, it can be used as only a simulation software, and it will provide a good reflection, a good simulation of the reality. Another point is that GNU Radio provides the production of a Python program by translating the GNU Radio processing blocks. And to listen to the radio, we will use this kind of program. So we can see that the output language is Python. It's very convenient considering that Python is a high-level language that is very versatile and compatible with a lot of devices. We will use first an Osmocom source block, which is a source block, a reference in the mobile communications. As Osmocom is also an open source project, so this block is not available in the default configuration of GNU Radio. We had to install it before. Then we use it, and we do the signal pass through a low pass filter. Then we choose the cutoff frequency to be the frequency of the radio station, which is 96 here. Then we calibrate the signal on the WBFM receiver that will say through the card that we have to receive FM data, and we stream the data to through the Ethernet cable with the TCP protocol at the address of the card of the board, which is 192, 168.2.2, 2.5555. Then to receive this signal, we have to use this program to listen. And this program, so the first program, the FM program, will be executed on the board, and we'll use the antenna and anything to receive the data. And this program will be on the PC, and basically what we will do is that we stream the data through the Ethernet to the PC, and then the PC needs to listen to the board. So this is a very simple program because it is just listening. Here we can have a graphical generate options that were deactivated on the first program because there is no graphical display on the board. So considering that we have only a listening program that is very simple, we just take the data that we streamed at the same address from the ZMQ subsource, and we stream it. We send it directly to the audio sync in the PC at 48 kHz. That is the frequency of usual CD quality sound. We use the ZMQ protocol to stream the data because ZMQ is a light and a fast library that allows programs to communicate with each other easily using the sockets. And this is a very simple protocol that we can use. And so when we do this, we have a lot of, we have the radio, we have the radio and we have the signal that is right, that is the 96 radio station, and everything works fine for us, and we will test it just after.
Now that we have done our research and that we have our program for the radio, you know that to listen to the radio through a Raspberry Pi 4, we must use software dedicated to the implementation of radio software and signal processing system. In our case, the most interesting things will be to use GNU Radio. But we cannot install GNU Radio directly on the Raspberry Pi 4. We need to install an operating system on a board that is small enough to be supported by it, which is why we are going to use Buildroot. Buildroot is a collection of makefile and patches that simplify and automate the process of building a complete bootable Linux environment for an embedded system. It will allow us to generate a Linux image implementable on the Raspberry Pi 4. For Buildroot and GNU Radio to work properly together, we will use our teacher GitHub folder. So to do this, we will start by installing Buildroot on your computer. So we go to the official Buildroot website and downloaded the file. Once downloaded, the first things to check is if the Buildroot contains the configuration for Raspberry Pi 4. Go to config and check Raspberry Pi 4 is here. Then we place Buildroot in the main directory of your computer. Thanks to the pbounce package manager, we can install GNU Radio and Osmo SDR package in our Buildroot. We don't forget to git clone our teacher's GitHub folder, which will allow us to get the right settings for GNU Radio and place it in the configs folder of Buildroot. The installation steps being done, we will now do a make menu config to check drop beer, which will allow us to communicate with the card thanks to the secure shell. Let's go target packages and networking application and drop beer. Let's check. We install JR aptX, which will be used later. And external option and JR aptX is check. These steps being completed, we proceed to make Raspberry Pi 4 64 GNU Radio dev config to build a consistent workspace in the Buildroot. Then we generate an image of the Buildroot with make. Once the image is generated, we use disk dump to copy the image to the SD card. After that, we mount the card to change the dynamic IP to a static one on this file. Finally, we can unmount and put the SD card in the Raspberry. The umount command is important to save the IP. From the PC, we go through the secure shell to try to connect the Raspberry Pi 4. under the predefined password is root. So we are connected and we can see everything works well. The card is now ready to use.
As for the connection, we have the power supply here. Then we have the Ethernet cable here, which will allow us to do the TCP/IP communication. Then the DVB-T dongle with this antenna, which will allow us to receive the radio. And finally, the SD card containing the Buildroot on the back of the RPE4.
Now, we reuse the GNU radio program that we saw at the beginning of the explanation. To do this, we compile the FM reception program, which will give us a Python program that we put on the card and that will run on the card. In parallel, we run the listening program on your computer.
Let's go for the test.
Okay, so 3, 2, 1.
Okay, fine. But turn the music down.
Okay.
Okay, it's louder, isn't it?
I don't think it's louder. I think it's I think it's fine. But once we did this, don't you think that we can go maybe a bit further than this? Maybe for the quartz or something?
Okay, yes.
Yes.
Go.
Let's go. Okay, so just to go a bit further this time, we want to study the transfer function of the RPI4. To do so, we will analyze the spectre of the RPI4, listening to itself to see where energy is consumed or not. The first thing that we will do is to generate a noise. And we can see that this is a uniform noise source that we will send to an RPI-TX sync at 200k sample by seconds sample rate because of the thing is that this is the maximum value that the DMA will accept. Beyond this value, the samples are not quite right. The data are just doing anything but what we want. We set the carrier frequency at 86.6 megahertz. This is what we want because we will see later that we will add because this value of frequency is time 5, which will give us 434 megahertz. And with this frequency, we can be sure that we cover all the industrial, scientific, and medical bandwidth. So after we did that, we will have to stream the data. The output language is still Python, and we don't have any graphical generate option because of this program will be executed on the board on the RPI4. So once we have done the noise, we'll have to stream the data, and then we have the same parameters, except that the sample rate is 2.4 mega sample by seconds. This is because we have 5 times 200 kilo sample by seconds. So for time 5, it does 1 megahertz, and in order to sample properly the signal, we have to go twice the 1 megahertz limit of the to avoid aliasing. We need to have at least 2 megahertz sample rate. So this is what we did here, and we still have the Osmocom source that we used before. we see that the frequency is 434 megahertz. That is 5 times 86 carrier frequency that we had before for the noise. And then we still use the zeroing queue pub sync that we used before, always with the TCP Ethernet protocol. We are using the same address, we are using the same protocol, and the only thing that we modify in the Osmocom source is this little radio frequency gain of 7 to have proper results. Now we will listen to our card and to our signal by using this program. It's a bit more complex than what we did for the FM receiver. So we have generate option which is graphical. This is what we have the Qt GUI here. We still have the same sample rate than before. We receive the data like before from the ZMQ, except that this time I've chosen to display it in a frequency sync and to vector sync after the fast Fourier transform. So the signal coming from the ZMQ pub source is transformed into a vector in order to do the FFT. We transform it to a vector of 1024 points. So this is why the FFT size is 1024. Then we square the value of all of this FFT to avoid negative value. Then we add 10 times log 10. So it will do just 10 times of the value we have to increase the difference in the magnitude of our values. And then we choose to display it in a graphic, in a vector sync graphic. So now we will test this program. So it was already uploaded on the card. I uploaded the first program, which is noid.p that we will execute using Python 3 here. Let's execute it. And then we will stream the data with a second program, which is called rtlextra.p. I will execute it too. So we have consistently to the documentation, we have this SDRAM and thing that is displayed. So this is right on the GitHub. This is what we choose to display in order to see that everything is working well. Just enter to quit. So this is simply what we said in the Python programmation. Here we executed the streaming using Python 3.2. We have all of these instructions that are quite what we have to do to think that everything works well. And then we have here the noise, here the streaming of the data, and then we will try to receive the data here. So we execute the program here. And what we see first is the results of the frequency things that we have here, and then the FFT, the result of the FFT at the second part. I'm not getting why it's not working here, because it worked before, so maybe we will wait a bit. Okay, so I had to execute again the program because the one before was not working, but for any reason when I do it again, it works. So we can see that there is a first transfer function here and a second transfer function. This is where the energy is consumed by the board, and this is where we can see the resonance are in our device. So we can see that the value of the resonance are almost from minus 400 megahertz and plus 300 almost 300 megahertz, 324 megahertz almost. And in the first one, that is this frequency sync, we see nothing because we are supposed to have a little peak at 86 or 434 megahertz, but it's not appearing, so it's a bit useless. But what is important here is this graphical display of the frequency, where we can see the true resonance frequency and of our device. So in this During this project, we had a lot to learn about embedded electronic systems. As a conclusion, we can say that in this project we were able to modulate, generate, and transform radio frequency signals using the RPI4. We also used some internet protocols like TCP/IP to enable client-server communication. And we were able to install an embedded operating system with useful softwares as GNU Radio to build a convenient workspace in the Buildroot part. And we learned a lot during this project, which contains everything. We think that it contains everything that will be useful for us in our future career.